Diode transistor logic is a class of digital circuits that is the direct ancestor of transistor logic. It is called so because the logic gating function is performed by a diode network and the amplifying function is performed by a transistor. Implementations. The Dtl circuit shown in the picture consists of three stages: an input diode logic stage, an intermediate level shifting stage, and an output common emitter amplifier stage. If both inputs A and B are high, then the diodes D1 and D2 are reverse biased. Resistors R1 and R3 will then supply enough current to turn on Q1 and also supply the current needed by R4. There will be a small positive voltage on the base of Q1. The turned-on transistor's collector current will then pull the output Q low, usually less than 1 volt. If either or both inputs is low, then one of the input diodes conducts and pulls the voltage at the anodes to a value less than about 2 volts. R3 and R4 then act as a voltage divider that makes Q1's base voltage negative and consequently turns off Q1. Q1's collector current will be essentially zero, so R2 will pull the output voltage Q high. Discrete. The IBM 1401 used Dtl circuits similar to the simplified circuit IBM called the logic complemented transistor diode logic. CTDL avoided the level shifting stage by alternating NPN and PNP-based gates operating on different power supply voltages. The 1401 used germanium transistors and diodes in its basic gates. The 1401 also added an inductor in series with R2. The physical packaging used the IBM standard modular system. Integrated in an integrated circuit version of the Dtl gate, R3 is replaced by two level shifting diodes connected in series. Also, the bottom of R4 is connected to ground to provide bias current for the diodes and a discharge path for the transistor base. The resulting integrated circuit runs off a single power supply voltage. Speed improvement. The Dtl propagation delay is relatively large. When the transistor goes into saturation from all inputs being high, charge is stored in the base region. When it comes out of saturation, this charge has to be removed and will dominate the propagation time. One way to speed up Dtl is to add a small, speed-up capacitor across R3. The capacitor helps to turn off the transistor by removing the stored base charge. The capacitor also helps to turn on the transistor by increasing the initial base drive. Another way to speed up Dtl is to avoid saturating the switching transistor. That can be done with a Baker clamp. The Baker clamp is named for Richard H. Baker, who described it in his 1956 technical report, Maximum Efficiency Switching Circuits. In 1964, James R. Beard filed a patent for the Schottky transistor. In his patent, the Schottky diode prevented the transistor from saturating by minimizing the forward bias on the collector base transistor junction, thus reducing the minority carrier injection to a negligible amount. The diode could also be integrated on the same die. It had a compact layout, it had no minority carrier charge storage, and it was faster than a conventional junction diode. His patent also showed how the Schottky transistor could be used in Dtl circuits and improve the switching speed of other saturated logic designs, such as Schottky TTL, at a low cost. Interfacing considerations. A major advantage over the earlier resistor transistor logic is the increased fan-in. Alternatively, to increase fan-out of the gate, an additional transistor and diode may be used.